Okay, in this lesson on concurrency in Zio, we're going to look at some functions you can use instead of fibers. Now, after all the videos I just did on fibers, why shouldn't I use fibers directly, or why shouldn't I use them all the time? And even though fibers are a nicer abstraction than things like threads and other concepts we could use, they're still relatively low-level building blocks. So in Zio, we have higher level combinators and a simplified concurrency and a definitely reduced boilerplate. And I compare these functions that you're about to see to the methods in the Scala collections classes. So with those collections classes, we use methods like map and filter and so on instead of writing our own custom for expressions. And here we do the same thing. We'll use the combinators you're about to see instead of writing low-level fibers. In addition to handling parallelism, a couple other nice things to do for us is they handle errors and resource management. And both of those are big productivity gains. So the general recommendation is to use fibers only for advanced cases where you definitely have to write a lot of custom code. Otherwise, try to use these high-level combinators you're about to see. There's at least 5 key functions that I'd like to look at. Zip_par is the first one, and we use that when combining 2 independent computations or 2 independent effects that we're going to run in parallel. And you'll see what I mean by that in just a few moments. Collect_all_par is a bit more advanced than that. It lets us run as many effects as we need to in parallel and then collects the results. Race is a function for racing 2 competing effects against each other, and then we use the winner from that race. And then race all isn't limited to 2. It lets us race as many as we need and gets the first success from that. And then for each par is for transforming collections in parallel. So this is one that does not take effects as input. It takes something like a list or any type of iterable. And then inside of a transformation function, you'll be working with effects in there, and then those will be run in parallel. And you'll see what that means in just a few moments. So zip_par is going to be the first one we're going to look at, and as I mentioned, it combines 2 effects in parallel, and when it's finished, it returns a 2-element tuple of the results. So you can see the way that works here. I have one value I named hello. It is a Zio effect, and it just returns the string hello after 2 seconds. And then Scala is the second variable. It's also a Zio effect, and it returns Scala after a delay of 2 seconds. And the way you use zip_par with this is you could say hello.zip_par Scala, or you could say scala.zip_par hello. But in this case, I have hello.zip_par Scala. And remember that this is a Zio effect, so nothing happens yet. But when this is run, after about 2 seconds, we'll end up with this 2-element tuple down here, containing hello as one string and Scala as a second string. And I want to emphasize the 2-second total, because if these ran sequentially, that would take 4 seconds. But because I'm running these 2 in parallel, it'll take about 2 seconds total. Next, collect_all_par runs multiple Zio effects in parallel and collects all of their results. And with collect_all_par, if any effect fails, the entire operation will fail. The way this works is here you'll see that I create a list, and this is a list of Zio effects right here. And then you can see here all 3 effects succeed. They have values 1, 2, and 3. Each has a delay time of 2 seconds. So this list variable is named tasks. And now I can come down here and run this list of Zio effects in parallel. That's what collect_all_par does for us. It runs those in parallel. And then after about a total of 2 seconds, it will return this list of 1, 2, 3. The next function is called race, and it runs 2 effects concurrently. Essentially, we're racing the 2 against each other. Here's an example that shows the first variable is named fast. When it succeeds, it returns the string fast, and it runs in about 1 second. The second variable is named slow. When it succeeds, it returns the string slow, but that will take about 3 seconds. So the way you race these then is you say fast.race slow, or again, you could say slow.race fast. In either case, when this result is run, the result will be the string fast, and you'll get that in about 1 second because it returns in about 1 second. And that's what we mean by racing, is that we get the result from the first effect that successfully completes. In this case, as long as one effect succeeds, you'll get a result from that effect. But if both effects fail, race will return the error from the first one that fails. The next function is race all. It races multiple effects. And by that, I mean you can race 2 or more effects. You could race 3 effects, 4, 5, 6, whatever you need to race. And just like the race function, it's going to return the first one that completes successfully. And the way this function works is a little interesting. It takes one effect here, slow, and then it takes all the others as an iterable. So you can see I create slow. It's an effect that succeeds with the string slow after 3 seconds. And then the others are a list of effects. So this one is named fast. It returns in 1 second. This one's medium, runs in 2 seconds. So you can see then I give the first effect here, slow, right there. You pass that into race all. And then the second parameter is this list, or again, any sort of iterable for the second parameter right here. And then when you run these, and remember that this is just an effect right now, so then when you run these later, the result is going to be fast, and that will return in about 1 second because fast has that runtime of 1 second. That for each par is the fifth function we're going to look at. For each par transforms a list of elements in parallel and collects the results. A unique thing about it is that it works on a collection of values rather than a collection of effects. And I have one example. It could be processing a list of files in parallel. But what we're going to do is just create this list of integers right here, 1 through 5. And then the way this works is you call for each par, you pass in that list right there. And then in this area between the curly braces, you just create whatever function you need to operate on the elements in that list. And then what you're doing inside here is creating an effect. So you can see I take in n. So in the first case, n is going to be 1. And then I say 0 succeed 1 times 2 and then delay for 2 seconds. So then this code goes off and it starts running in parallel. And then for each par says, okay, now work on number 2, then work on 3, 4, and 5. Then all 5 of those will be running in parallel. And because each of those takes 2 seconds and they're run in parallel, we're going to get a result in about 2 seconds. And that result is going to be a list of 2, 4, 6, 8, and 10. So there's even more concurrent functions, but I just wanted to cover those initially because I think they're the main ones. A few other ones here, collect all successes par. This one runs all the effects you give it in parallel and then collects only these successes. And I have an example of that coming up in just a few moments. For each par discard is like for each par, except it discards the results. So this is typically when you're going to be doing something that has a side effect that's returning unit, so you don't care about it. So this is going to be a little bit more efficient than for each par because it knows that you just want to discard the results. Reduce all par is like the Scala reduce method, and it reduces a collection of 0 effects, again, in parallel. And then merge all par is like the Scala fold function, and it merges all effects in parallel, and it starts with an initial value or an initial seed value that you give it. So let's take a look at these. The first one is collect all successes par. So you can see what I have here is I'm creating this list, and it's a list of 0 effects. So I have succeed with 1, fail with error, succeed with 3. So that creates that list, and then I pass that list into collect all successes par. And then you can see what it does is it does collect those successes. It only collects these successes. So it collects that one, and it ignores that one right there. So this can be really nice when you know that you have a list of effects and some of them might fail and you're not really interested in the ones that will fail. You're just interested in the ones that succeed. And then the next one is for each par discard. And as I mentioned, you want to use it when you're having some sort of effect that doesn't return any meaningful value over here. So generally that's going to be an effect that returns unit. So you can see here that I call for each par discard, have that list of 1, 2, 3. I'm going to print each one of those. And I need to note that they're going to print in parallel. So you may get 1, 2, 3 here, you may get 2, 1, 3, or something else because they are running in parallel. After that, we have reduce all par. It's used to reduce a collection of 0 effects and do that in parallel. And when it's finished, it results in a single reduced value. It works by combining the results in parallel using a specified binary operator or operation that you're going to be giving that, and we'll look at that in just a moment. But that can be things like sum, concatenation, etc. It starts with the first element in the list and reduces all remaining elements based on your binary operation. So let's take a look at this. So here's a list of 0 effects I'm creating, similar to before. So 3 effects with the values 1, 2, 3. The delay times are different. They're 2, 3, and 1 right there. Then what I'm going to do is call reduce all par, and I give it an initial seed value right here, and then I pass in the list of effects as a second parameter right here. So I'm going to assume that you've seen reduce before. So the function starts with this curly brace, ends with that curly brace. Can be whatever you need it to be, but in this case, we're doing a sum algorithm. And I've shown this before in previous courses. But one key here is that all of these steps run in parallel. And then a second key is that reduced here is going to, again, be a zero effect. So it doesn't do anything right away, but once you do run it, such as in a for expression or with flat map, once you run it and you get that result, you'll see that the result is going to be 6. Then merge all par is the next function we're going to look at. It merges all the effects in parallel, also starting with a provided initial value. It combines each effect's result using the specified binary operation. Again, we get a single merge value that's based on the combining function. And it runs all of the effects in the list concurrently, combines the results in a thread-safe manner. And a key probably with both of these functions is that the order of completion of the effects is not guaranteed because they are run concurrently. So in this case, I'm creating a list here, and this will be hello, comma, world. But what I'm doing is I'm saying this one's going to take 3 seconds, that'll take 2, and this will take 1. Then in the next step, I call merge all par, and I pass in the effects here as this list right there. Then I pass in the seed values. So again, this is similar to the fold function in Zio where you pass in a seed value. So if you haven't seen this type of thing before, you'll want to go back to some of the early videos where I talk about fold and reduce, and I talk about providing a seed value. And this is generally an identity value. So when you're doing string concatenation, the identity value for string concatenation is a non-empty space like this. But anyway, get back to merge all par. We pass in the list of effects, we pass in the identity value, and then our algorithm here is going to be a sum or a concatenation algorithm right here. In this case, it's concatenation because we're working with strings. If we were working with ints, this would give us a sum. Again, the merged effect is a zero effect, so nothing happens yet. But when you do run it and you get the result and print it out, in this case, because of the delay times up here, the result is going to be world, comma, hello. And that's because the world runs in 1 second, the comma runs in 2 seconds, and then hello runs in 3 seconds. So that's what I want to be really clear about. When you do something like this, the order in which you get the elements back is not guaranteed. So of course, that's really important for string concatenation. Another thing you do with parallel collections is control the number of fibers that are used. So in Z01, we had things like collect all par n for each par n. And in those, you could specify the number of fibers that were being used. In Z02, we use with parallelism and with parallelism unbounded. And what I mean by this is an old function call would look like this, where you'd say, well, I want to do for each in parallel, but only use 8 fibers, and then download all these URLs. And the way you do that with Z02 is you write the initial code like this, and then you add the with parallelism to the end, and you say, we'll do that with 8 fibers in this case. Or you could also say in this case, don't put a maximum number on the fibers with parallelism unbounded. So that's a way you could do that with for each par. And then this example here is going to show how to use that with collect all pars. So you start off with a list like I showed before. Now we say Zio with parallelism of 2. Again, this could be 4 or 8 or whatever makes sense for your computer. But with parallelism of 2 in this case, run collect all par on this set of effects. So that's the preferred way to do things in Z02. And there are still a couple of functions that have a par n. So you have collect all par n discard and for each par n discard. At the time of this recording in October of 2024, these functions are still available in Z02. Now, when you should use with parallelism is like any other time you're optimizing parallel and concurrent code. So you're trying to prevent overwhelming of resources like CPU, RAM, disk, or external services that you're working with like database connections. You may also want to do it when you're working with a system that has rate limits. And then when you're fine-tuning performance based on what you know the system capabilities are. So all of this right here means, hey, we have some parallel and concurrent code that we've written, and now we want to take some time to try to optimize it based on what we know about the systems that we're running on. And again, for that, we use with parallelism. So to give this a summary, these are the main functions we looked at: zip par, collect all par, race all, for each par, and then I just mentioned with parallelism for controlling that. And also noted we had a few other concurrent functions we can use for specific use cases. And now in this very last slide, I give you a summary of all the functions that we just covered. So I'm not going to go over all of these, but as I was just looking at this, I just realized I didn't cover this when I talked about zip-par. So one thing you can do with zip-par is when you have two effects and you zip them together to create that two-element tuple, you can merge or transform them using map and then whatever algorithm you want to pass into map. So I just wanted to note that I didn't cover this part, but I believe I covered everything else here. So I'm not going to go over all these in detail again, but I hope this can serve as a nice reference and comparison tool here at the end of this video.